All right, so we're going to cover page 7 and 8 of the notes from section 7.1. Before we do, I want to go back to the problem that we were working earlier and use it to kind of motivate the idea. So remember, earlier we were talking about a 3-inch second hand, and it goes 25 seconds. So an amount of time is going by. And based upon that, we're going to be able to turn the angle that we know that the second hand goes into an angular speed, and the distance that the tip of the hand of this or the second hand travels into a linear speed. So we knew it went 25 seconds, and we calculated that this using 25/60 times 2 pi was 5 pi over 6 radians. So if we want to think about some kind of angle speed, we know that it goes 5 pi over 6 radians per 25 seconds. And then, of course, that's 5 pi over 6 multiplied by 1 over 25, and that's in radians per second as a unit. And then the 5 and the 25 cancel, and we end up with pi over 30 radians per second. So pi over 30 radians per second, so pi radians per 30 seconds, which hopefully makes sense for a second hand, right? Because it takes 30 seconds to go halfway around, which is pi radians. And we can talk about the rate that the angle of the second hand is changing as pi over 30 radians per second. The other thing we know is the arc length here, the distance that it travels, and using the 3 inches, that we know that the radius of the second hand is, and the arc length that it the angle that's subtended of 5 pi over 6, we can calculate S is equal to 5 pi over 2 inches, which is about 7.8 inches. We check that to make sure that it makes sense, but we want to keep our values exact here. And so if we want to think about linear speed, we know that it goes 5 pi over 2 inches, the tip of the hand, per 25 seconds. And that is equal to pi over 10 inches per second. And we can get a decimal approximation of that, which is about 0.3, just to kind of have it in context. So it goes about 0.3 inches per second. All right, so now that we have the basic ideas of incorporating an amount of time that's gone by, whether, obviously a second hand, minute hand, hour hand moving automatically builds time and angle, and if we know the length of the hands, we can all do all these problems just based upon knowing the rate at which they are traveling or changing. But other applications, let's see, let's jump in here, page 7 of the notes. Let me double check, make sure. Yep, so a vinyl record. All right, so we want a vinyl record playing on a turntable, rotating clockwise 45 rotations per minute. And we want to find radians per second. So we know that it goes through 45 rotations per 1 minute. Well, it may not feel like it, but rotations is an angle. It's buried in there because remember, we have a fact that we know. That's that one rotation is equal to 2 pi radians. And so we can convert rotations into radians and use that converting factor right there. And we want rotations in the denominator, so 1 rotation and 2 pi radians. And so now with the cancellation of rotations, we're in radians per minute, and we're getting close. Remember, our goal here is in radians per second. So the next thing we need to convert, and the next fact we need to use, is that 1 minute equals 60 seconds. And we can use that here, and we have minutes in the denominator in the first thing, so we're going to want to put minutes in the numerator there, and seconds in the denominator. And so 1 minute and 60 seconds. Great, and then we can cancel minutes and minutes. And when we do this math, we get 90 pi over 60. And that's in radians per second now, and that can simplify down into 3 pi over 2 radians per second. So 3 pi over 2, right? So that's 3/4 of the way around per second. And you do that for, well, whatever, let's not overly generalize to the specific record, but we can interpret that as an angle that's passed and how long it takes for the record to pass through that angle. All right, so that is angular speed as an example, and then for linear speed, we have a bicycle wheel that's got a 28-inch diameter. Be careful there, being given the diameter, not the radius. And so the first thing we're going to probably need to do is calculate the radius using the diameter. Tachometer, which measures the rate at which things spin, determines that the wheels are rotating at 180 rotations per minute. Remember, as soon as you know rotations per amount of time, it's a common way of describing the rate of something spinning. You can convert that, just like you saw, into a radians per unit of time. And so our goal is to figure the linear speed in miles per hour. So we need two things. We need the radius, not too hard because we have the diameter, and we need the radians per hour. Why? Because we want it in hours, and radians per hour times the radius, as we saw earlier, is going to give us some unit of time in linear speed per hour. So let's do that. The first thing we'll calculate here is the radius. And that radius is r equals the diameter divided by 2, which is 28 over 2 inches, or 14 inches. Great. And then the second thing we need is in radians per hour. We need to be able to describe you can never describe the linear velocity without the angular velocity. So in the last problem, we stopped because all it wanted was the angular velocity. In this problem, we need to continue on after that to get the linear velocity. And so in radians per hour, I could do radians per minute, radians per second, right? But I'm going to do radians per hour because I want hours in the denominator eventually for my linear speed. So we know we have 180 revolutions per 1 minute. And we can use the fact that 2 pi radians is 1 revolution, and our revolutions cancel, and the fact that there is 60 minutes in 1 hour, and then our minutes cancel, and we end up with 21,600 pi radians per hour. Great. So now the third thing we want to do is find the linear speed. Well, we know that the angular speed is 21,600 radians per hour. And we know that the radius is 14 inches. And so that's going to give us inches per hour. And so we have 302,400 inches per 1 hour. But we want that in miles per hour, so we're going to need to convert inches into miles. And then we can use the fact that 1 foot is 12 inches. And the fact that 1 mile is 5,280 feet. Now the feet cancel, the inches cancel, and we're in miles per hour. And when we do that math, we get 105 pi over 22 miles per hour, which is about 4.8 miles per hour, a reasonable speed for a bicycle to be traveling. And then, of course, it's an application, so we need a complete sentence. The bike is going about 4.8 miles per hour. Great. All right, so for the 2 practice problems, so you have some practice and can know if you are on the right track or not down here. For the page 7 practice, you need radians per second and radius. Sorry, which page am I on? Back to page 7 here, right? Yep, back to page 7 here. So the child is spinning the rock. You should be able to make a note here for yourself, 240 pi radians per minute. The map there, the first thing you're going to need to find, of course, is in degrees per minute, the angular speed, and then you can convert that into radians per minute. And then for the practice on page 8, the Carnival Ferris wheel with a radius of 30 feet. We want to be able to talk about the speed that someone riding it is going, someone at the very edge of it, in feet per second. So make sure that when you finish with your unit conversions, you get about 2.7 feet per second is the answer you're looking for. Of course, you're going to need to find the radians per second because you want seconds per as your time, and then you can convert that into linear speed just using the provided radius.